Alright, welcome back to an addendum video to my last video, where I gave an incorrect Lagrangian density that I decided was important enough to correct. So this will be a Lagrangian density of all known physics, and then some. I'll throw in a little extra information at the end. And this will be the addendum to my video entitled An Elegant Structural Overview of Modern Theoretical Physics, where I start with classical electromagnetism and we build up to modern Yang-Mills theory, and then we go into gravity and beyond. So, this Lagrangian was formally peer-reviewed by Dr. Garrett Leasy on his own terms. We did a lot of work back and forth, making sure that everything was kind of like congruent with reality. Like if I wanted to plug this into a path integral, if I wanted to do a Feynman path integral, this would yield correct results. And so we don't want to just conceptually understand this, right? We want to see what equations physicists are actually working with. So we'll start with this idea of constructing the universal Lagrangian, the unified Lagrangian density that gives us all known physics. But we're going to start with just trying to build the standard model Lagrangian, as it's so called. So we'll perform a simplified construction of this Lagrangian density by summing together the Dirac, Yang-Mills, Yukawa, and the Higgs Lagrangian densities. So this will start out with a Dirac Lagrangian that's source free. This is a free field Lagrangian here, in regards to spinor fields, and a potential mass term if necessary. Now we have just the covariant derivative with the gamma matrices. We're not worrying about particular charges. We're not talking about particular connections with other fields. We just want the free field Dirac Lagrangian in its general form. So now we take the U1 sector of our three available Yang-Mills symmetry groups. If you think of the standard model Lie group SU3 cross SU2 cross U1, we're just going to take this U1 part, and by merging this with the Dirac density, we form the free field quantum electrodynamic Lagrangian. So we have an electromagnetic vacuum and other things going on here, for which spinors can be a potential arising of the dynamics. But there's not an actual official connection here, and there's no actual gauge solution here for interactions. We're going to add that, a general gauge invariance across the system, without any particular source charge. So this partial derivative that you saw above is generalized to a covariant derivative, and with spin covariance more specifically, as well as other interaction terms for fields overall, because we're going to have more fields such as the gluon fields. We're going to have the W, Z boson fields. We're going to have all these different things. So we're going to go ahead and just throw in a general term, and we have that little zeta there in the bottom half of that 1 over 2 zeta of that covariant derivative of a potential all squared. That zeta term is the constant that we select to determine which gauge condition we're actually interested in. So by extending the symmetries and interaction terms corresponding to the full SU3 cross SU2 cross U1 group, we obtain a standard model Lagrangian density where these anomalous quote-unquote ghost fields emerge from our theory. Now these are non-physical degrees of behavior that we want to eliminate in our theory. And a priori, because a lot of non-abelian tension comes to our notion here because of SU2 and SU3, we're going to need a little bit more than just a gauge selection term. We're also going to need Faddeev-Popov ghost fields to counteract these terms. But we don't have those included yet, so we just have our actual standard model Lagrangian density with a generic gauge fixing term. But that's not the full gauge fixing potential that we need. We also need Faddeev-Popov fields. And that's exactly what this term will be right here. So electroweak theory and quantum chromodynamics promotes our theory to a generally non-abelian context. And so we're going to need these additional terms to cancel out when we do integration. So here's the standard model Lagrangian, where we're going to have all of the actual gauge fixing terms we need, Faddeev-Popov ghost included, and then we're going to set that Higgs potential via phi. Notice here we don't have an explicit minus MC. This is already included within all these different things involving the interaction terms, the Yukawa potential, and the spinor function psi. The next step then is to condense this whole Lagrangian density and assume that we're going to perform gauge fixing when we actually do integration. So we can indeed make this look a lot prettier. Kind of using a more tensorial notation explicitly here and then just condensing it in by assuming that we do gauge fixing. You can certainly agree that this is at least a simpler equation. But with spin covariance included in the generalized derivation operator, and by having the metric itself of spacetime consumed under path integration, we can include gravity by adding the Einstein-Hilbert Lagrangian density to the standard model. This yields a unified Lagrangian density, which has all energy terms of known fundamental principles of physics as it stands. And that Einstein-Hilbert Lagrangian density is given by h bar over 16 pi a sub p, where a sub p resembles the squared Planck length or a Planck area. And this is all in proportion to the original Einstein constant, that being 8 pi g over c to the third power. But this r is the Ricci curvature scalar, and then we have lambda here for dark energy, the cosmological constant term in general, associated to the volume of the total manifold of spacetime. So the stationary action of all known fundamental principles of physics can then be expressed as the following integral. And later you will see that we're actually going to promote this into a partition function to give us the Feynman path integral. So we're going to expand the unified stationary action in terms of this integral formulation. And we're going to include gauge fixing terms, which gives us the following. Now we're integrating over square root and negative g across all of the terms, because g is the determinant of the metric tensor. So as we continue to expand these terms, here comes the Yukawa and Higgs terms here, for example. Let's move on to the third line now, where we see now our gauge fixing terms, and then the Einstein-Hilbert sector being integrated over spacetime. So all of this is being integrated over spacetime, and it's being multiplied by the square root of negative g, g being the determinant of the metric tensor itself. So this is a stationary action of pretty much everything that goes on in spacetime as far as we currently know it. So we can vary that stationary action using this functional variation. So the variation of s is equal to 0. You nudge the system, it's invariant. I mean, this is just a statement more or less kind of condensed from the notion of conservation of energy itself in a more global perspective, in the sense that the system you start with is the one you end with, and everything that can happen does happen. And we shall recall that all this information that we're actually varying comes from the following Lagrangian density. And that's that universal Lagrangian, which is the sum of the standard model using spin covariant functionality plus the Einstein-Hilbert sector for gravity. We can take our stationary action with this condensed notation to establish a path integral formulation of all known physics as well. And so we're going to bring back that stationary action, recalling that we're integrating over spacetime. That d4x is our hypervolume differential for spacetime, and square root of negative g, g being the determinant metric tensor, multiplied by the unified Lagrangian. So square root, negative g, and the unified Lagrangian are our integrand that we are integrating over spacetime. That gives us the stationary action. So under the path integral formulation, we want to introduce a phase factor using Euler's exponential. That's going to be e to the I theta, where now instead of theta, we're arguing for the action itself. That's going to be your phase parameter. That's really going to alter the dynamics. So your argument is the standard model Lagrangian inside of a phase that's being integrated over a functional. So here we go. Check this out. So the functioning of the partitioning alone can be achieved with another integral of a functional. But the inclusion of Euler's exponential function frames this in terms of a phase factor, which I more or less hinted at. So at this point, the wave function collapse is no longer the focus of how we obtain classical physics from quantum mechanics. Of course, barring quantum gravity, since we're not discussing that right now. The Feynman path integral formulation of this theory takes into account all the possible histories and field histories, and then also their combined contributions towards a single classical principle of least action. So all of your quantum probabilities cancel out and lead to a classical action. So this is not just all known current physics, but it's more or less actually a generalization of that notion under Hamilton's theory of continua with respect to the Lagrangian formulation of dynamics. And this is that partition function. This is indeed related to an inner product of Dirac notation of our actual function. Of course, we don't see any Dirac notation here. We're just using Feynman path integral notation explicitly. So d of phi is the functional overall field. That's our actual measure that we're actually integrating over in this case. And you can see here Euler's a constant e to the I. Now normally you had e to the I theta equals cosine theta plus I sine theta. But what we have here is cosine of our functional in terms of our variation plus I sine that same functional. Now let's consider general operator algebras and the idea of Lie algebras in regards to this standard model. So the Yang-Mills Lie group that we're concerned with, SU3 cross SU2 cross U1, is a manifold that we call capital G. And it's a Lie group because it's both a group and a continuous manifold for which we can infinitely differentiate across all points. But at the identity element, wherever that may be defined on that manifold, there exists a tangent space, and that tangent space is the Lie algebra that generates capital G, the Lie group. So T sub I of G is the tangent space at identity of the manifold G, and that's the direct sum, a Lie algebra SU3 plus SU2 plus U1. The spectral triple, A, H, and D, where A is a general operator algebra or a general algebra in context, such as the C-star algebra and things like that, or H in this case is the Hilbert space, or we can consider D the Dirac operator. These things form a spectral triple, a form of a geometric invariant, if you will. And this operator algebra A is actually quite interesting, because within it we have the C infinity of M. So we have a particular C-star algebra of continuous functions over a manifold M. And then we have this finite, generally non-commutative algebraic extension with the complex numbers and the quaternions and the rank 3 complex matrices. While the Lie algebra describes the generators of symmetries, as you may know if you've gotten this far into math, the operator algebra describes not only the space of smooth functions on a Riemannian, symplectic, or otherwise, more general manifold that we're interested in. So it could be Lorentzian, for example, but then also the ways in which we can encode Lie symmetries within our greater theory, hinting that gravity and quantum theory may arise from the exact same spectral data. So the role of associative operator algebras becomes very important here, and it may be the unifier of quantum theory and gravity to some degree. We don't know exactly how deep we're really wanting to get into this yet. There's a little bit of limbo and some questioning of how we solve particular problems and a meaning of particular tensors once you start getting to this level of discussion. And you even need, in some cases, higher derivative theories of gravity in general to even make sense of this. Many in which cases we don't really have a proper formulation of in all cases. So let's consider now what we do have so far though. A spectral triple A, H, and D, where A is a general operator algebra, C star, which in this case star is infinity, so C infinity of M, cross C plus H plus M sub 3C. where H is a Hilbert space given by an L2 space in terms of a manifold and a spinor bundle S. And that's given with a tensor product of the fermionic degrees of freedom of these Hilbert spaces or Fock spaces. So we have this L2 space tensored with the fermionic degrees of freedom. That gives us the whole Hilbert space that we're interested in here for our theory. And then we have the Dirac operator that acts on the Hilbert space. In this case, we have a geometric part of the Dirac operator tensored with the identity element, plus the gamma 5 identity element of the Dirac algebra tensored with the internal degrees of freedom of the Dirac operator. This is important also for various gauges. But first we'll express what this finite extension algebra, which is C plus H plus M sub 3C, encodes in respect to our theory. How does this relate to Lie algebras and Lie groups? Since the complex numbers are a field, their derivation algebra is trivial, so we won't really go deeply into that. So here's our derivation of C. The complex numbers are well equipped to encode what we need to generate U1. Many people who have gotten this far in physics are well aware of the classical context of electrodynamics and the importance of U1 by this point. So it becomes more interesting when we get non-trivial extensions. So let's consider, for example, the derivation algebra of the quaternions, which are indeed non-trivial. This gives us an immediate Lie algebra structure in terms of SO3, which is isomorphic to SU2. So the special orthogonal 3x3 matrices are in many ways equivalent to the special unitary metrics of 2x2 matrices, which can have complex values. So that's the derivation algebra essentially of the quaternions. It's essentially encoded within SO3, which is isomorphic to SU2. Now SU2, the group, is generated by elements of the SU2 algebra. Therefore, the quaternions are equipped to encode what we need for the Lie group manifold SU2, which gives us a third of that matching SU3 cross SU2 cross U1 manifold that we want. The derivation algebra for the set of 3x3 complex matrices is, of course, also non-trivial. So their derivation algebra is isomorphic to the general linear group, or in this case, the general linear algebra 3C. We use lowercase for algebras here, and uppercase for groups here, just to keep that, keep that in mind. A fundamental subalgebra of this Lie algebra is SU3, generating the Lie group SU3. So there you go. That's how this really relates to these different groups that arise from standard model physics. Because these algebras are the generators of those groups at the tangent space at identity of the associated manifold. So we're left with the algebra of smooth functions to consider now that we looked at that finite non-abelian algebra in general. Now we're looking at C infinity of M. If we let M be a general manifold, let that be Riemannian, Lorentzian, symplectic, etc., then C infinity of M is the algebra of all infinitely differentiable functions on the manifold M. And of course that's an enormously powerful algebra because that's like calculus. So it can pretty much be used to just describe space-time itself. Whether flat or curved is not even the point anymore. It is then the tensor product space that's formed by tensoring this commutative algebra, C infinity of M, and the general non-commutative algebra shown before. It becomes non-commutative due to the nature of quaternions in the 3x3 matrices. And this yields our generally non-commutative associated operator algebra of interest. So this operator algebra is ultimately a tensor product space unifying everything that encodes modern physics and then some using a more general mathematical notion. So this means that the very generators and functions that yield all known physics, as I had just stated really, are indeed unified by a single tensor product space. And this is really what we're working with when we're going into non-commutative extensions of standard model physics, when we're looking into things such as quantum gravity and perhaps even beyond that. So this is an important algebra, if not probably one of the most important algebras in physics right now. We also consider the extended Dirac operator acting on a Hilbert space with a spinor bundle assigned to it. Remember that was L2 of M and S. And then we have the Dirac operator acting on that Hilbert space. This all combines to generate a geometric invariant when we consider the context of this algebra as well. And that's where we get our spectral triple. And that completes what we need for a unified spectral action principle. Because as we vary a geometric invariant, and the geometric invariant we'll call S, we must obtain a zero function, or else it's not a geometric invariant by definition. So now we wish to evaluate the spectral action for our unified non-commutative theory. We're going to go ahead and give this to you here. There's a lot more to this involving derivations and such that we simply do not have time to show in this video. For this presentation, we will only focus on performing an asymptotic expansion of the trace term to yield gravity, gauge field, and the Higgs field using the Seeley-DeWitt coefficients. These come from a heat kernel expansion, which are critical in modern theoretical physics. So we choose n equals 4 for our dimension constant since we're working over space-time. This yields the following. This to me is an absolutely beautiful series. A sub k of d squared are the Seeley-DeWitt heat kernel expansion coefficients acting on the squared elliptic Dirac operator. Lambda is a scaling parameter, and f is a general cutoff function that we're using to modulate eigenvalues for our expansion over spacetime. So these eigenvalues are going to need to be modulated in order to keep us congruent, depending on how we're flipping through different gauges, different dynamics, different symmetries. We're going to have modulating eigenvalues that we need to keep a congruent mathematical theory. Our first term of the series for k equals 0 corresponds to the cosmological constant term. But that makes sense because the zeroth component over something that gives you an integral over space-time is literally just the volume of the manifold itself. So whether that manifold is expanding or not is not the point, because you're just integrating over the volume of that manifold. If that volume is expanding, then you're integrating over that expanding manifold. Of course, we don't know a priori without experiment whether or not the universe is expanding or not. We've concluded that it is based on experiment, but that would not have been known without that experimental data. And so this is a more fundamental statement corresponding to cosmological constancy in general. The next interesting term is also an even term at k equals 2, corresponding to the Einstein-Hilbert action. This also makes sense, however, because a sub 2 of d squared corresponds to scalar curvature of a manifold in general. And well, of course, that's what the Ricci curvature scalar is for. And at the next even term, k equals 4, we find yet another interesting structure in terms of the Yang-Mills fields, F sub mu nu, F upper mu nu. These are the rank 2 Yang-Mills gauge field tensors. We also have other interesting kinetic and potential energy terms included in a sub 4 d squared. But of course, that just corresponds to the kinetic and potential energy terms of the Higgs field, which we can simplify based on our earlier expression. So we did not cover the fermionic part, we only covered the trace term as promised, but hopefully you can begin to get a glimpse of how the spectral action principle generates our current known laws of physics, and it exploits the commutative and non-commutative structures of our spectral triple. Given a spectral triple, S equals the trace of f of d slash lambda plus psi with d acting on psi, where d is a generalized Dirac operator. The variation of our spectral action must equal 0. This is the spectral action principle. This generalizes all known current physics. We'll see one of the multiple fundamental field equations of modern theoretical physics that can be attained by considering this fact that a geometric invariant in general goes to 0 under first-order variation. We'll begin with the Einstein-Hilbert sector of the spectral action that we generated under asymptotic expansion in terms of the Seeley-DeWitt coefficients in the heat kernel expansion formulation. The Seeley-DeWitt coefficients acting on the elliptic differential operator are themselves integrals of geometric invariance overall. But in this specific case, however, the variation going to 0 of both the zeroth term corresponding to the cosmological constant term we saw earlier, and the k equals 2 term we see above related to the Ricci curvature scalar, yields the Einstein field equations of general relativity. So the Ricci curvature tensor R sub mu nu minus 1/2 the Ricci curvature scalar R times the metric tensor G mu nu plus the cosmological constant times the metric tensor G mu nu equals the Einstein constant times the energy momentum tensor T sub mu nu. Well, everyone knows that. That's, of course, just the Einstein field equation of general relativity, but it's interesting to see how we can generate this under an asymptotic expansion in terms of a heat kernel. Higher order derivative terms such that exist in, for example, a sub 6 d squared lead to correction terms that are necessary for higher derivative theories of gravity. And these higher order even terms also correspond to normalization corrections in general to gauge fields and other principles. Further research may also implicate quantum gravity in relation to terms such as these rank 4 Riemann curvature tensor products, and, for example, a Laplacian of Ricci curvature scalars and, again, more general derivation theories. And these alone can just be found within the curvature sector of k equals 6. This doesn't include matter and all these other types of non-abelian extensions. There's a whole lot more going on than just the curvature sector, and yet we can see all of this just within that section. And by considering all orientations, we recall that this is an application of Stokes-Cartan theory, which we can generalize to the notion of distributional k-forms over potentially infinite dimensional spaces via the following. So we have an integral over our differential form in terms of evaluating over the boundary of a manifold. We're taking the integral of an n-1 form over the boundary of a manifold, and that equals, well, we have this negative 1 to the k. Ignore that for a second and focus on the integral on the right. That's an integral over the whole manifold of the exterior derivative of our n-1 form, which yields an n form by definition. So we've connected n-1 forms to how they classified n forms by just comparing the left and right side of this equation. And that's done by comparing the exterior derivative to the boundary operator from algebraic topology and differential topology. Very interesting to think about there, right? Now this negative 1 to the k here, we just choose k determining, depending on the orientation of the manifold that we're really wanting to integrate over. How are we wanting to orient our theory? So we just put a k here to indicate that this can flip between negative, minus, negative, or minus, so on and so forth. We just choose what we need. If we want to have the theory written in terms of a negative manifold integral or a positive one, that doesn't matter. This is all contained in this equation. So this is essentially all of calculus written in forms of an integral. But now we want to consider a local tensorial form of this equation that encompasses the divergence-free property of the curvature 2 form associated with the connection on the principal bundle. This leads directly to the Bianchi identity. So let F be a curvature 2 form of a connection on a principal bundle. We can write it in local coordinates via the following. We employ the wedge product between dx mu and dx nu. F sub mu nu are the components of the curvature 2 form. This looks a lot like the Faraday tensor components plus a commutator for potential. This works for various gauges. The exterior covariant derivative, not to be confused with the regular exterior derivative of the curvature 2 form, is 0. And this leads to an underlying catch of how all this corresponds to our prior discussions on physical principles, especially in terms of mathematical gauge theory in general. But this fact regarding the curvature 2 form that we've been working towards is really none other than the aforementioned Bianchi identity. And that states that the exterior covariant derivative of the curvature 2 form is equal to the exterior derivative of the curvature 2 form plus the potential wedge the 2 form minus the 2 form wedge the potential, and that equals 0. Now, a wedge f minus f wedge a is the commutator for the gauge connection and curvature, which is essential for our non-abelian extension to what otherwise would just give us Maxwell's equations in simpler forms as that. When we're extending beyond u1, we want these additional commutation relations. Since we use f sub mu nu for the components of a curvature 2 form, we can expand this Bianchi identity as follows, using explicit tensorial notation and not just the notation of differential forms as shown above. But it's all saying the same thing. The left three terms over here are abelian terms corresponding to the electromagnetic, or in the quantum case, photon fields. It corresponds also to classical or quantum complex scalar fields. It also corresponds to different applications in superconductivity, mostly more of the simpler cases, as well as weak field gravito-electromagnetism. It corresponds to various different adiabatic processes, certain protocols for quantum computing, and then, of course, various aspects therein of condensed matter physics itself. But there's so much more that this can cover. But it's when we jump to the non-abelian terms that we get our way more complex theories. And that's corresponding to, say, strong nuclear fields, such as the gluons and things of that nature, the weak nuclear fields, the electroweak nuclear fields. General Yang-Mills theories overall that may even generalize beyond our current known physics. This would, of course, include grand unified theories. This includes spin liquids, general applications of topological insulators, high temperature superconductor physics, and not just your simpler cases of superconductivity. Especially when you're going to need these more advanced asymptotic expansions in terms of heat kernel coefficients. And so this will lead in also to the ability of describing Einstein-Cartan theory, or quantum gravitational field theory as a general study, etc. So this is essentially all known current physics explicitly stated in various different ways. And that's really what I was hoping to achieve with my prior video, which gave an unfortunately incorrect Lagrangian density where there were a few mistakes, no less one in which I did not promote the Dirac operator to a general covariant and gauge covariant derivative or derivation operator, but then also the fact that I only applied the square root of negative g in terms of the Einstein metric, when really we needed to be integrating this over the entire Lagrangian density, or multiplying it into the entire Lagrangian density and then integrating over space-time. So hopefully I've corrected that with this video here, and I've given you a little additional information for the people that are more into the rigor and the advancements of modern math and physics, and hopefully I've calmed some discomfort